a transformer is. You just have a piece of metal and you have a wire. Of course, you can't just randomly use the piece of metal and the wire and then hope that it's able to control the voltage. No, it's not the random usage of this, but the intelligent usage. And this is why, once again, scientists and engineers get paid the big bucks, because they know exactly how to utilize these pieces of raw material. So let's go over the answer together. The piece of metal, you want the shape that looks like this. Essentially, you're making a donut, or a square donut. To it, you have your AC source, and that's going to be through a wire. So let's use that wire and make it go through like this. We're going to wrap the AC wire around one of the arms, or one of the sides. We're going to call this the primary side. The primary. On the primary side, it's going to be delivering a voltage called VP. VP. Even though this is alternating current, meaning the current's going to go back and forth, let's just say at this specific instance, the current's going to be in that direction, and if you follow it through, the current's going to be coming out over here. So this is VP primary, IP primary, right? P for primary. Now, what do you know about wires with current? One of the things that we discussed is that it generates a magnetic field. What did we just make by coiling the wire around like this? Solenoid. We made a solenoid. You guys remember the solenoid? Solenoids have a magnetic field that goes through the center of the spiral. Goes through the center of the spiral. Here, the magnetic field, using the right hand rule, where you put over, follow your thumb, the curl of your fingers is going to give you the magnetic field, and the magnetic field is going to be in this direction. This magnetic field can be dispersed throughout the entire conductive pole. So the piece of metal is here. The wire that we need is going to be over here in what is called the secondary. The secondary. With this wire, we coil it up in this fashion. We coil it up in like fashion. So here we're going to have VS as the secondary. Should I draw it? And at this instant, the current is going to be flowing in this direction. And this is going to be IS. Oh, actually, I already gave away an answer. Actually, I don't know. So, why did we wrap the coil around in this fashion? It's because, remember, a changing magnetic field generates a current. The primary is alternating current, so the current's going to go constantly back and forth, meaning the magnetic field is going to go up and down, up and down, up and down. So here the magnetic field is constantly changing. The magnetic field over here is going up and down, constantly changing. And we discussed a changing magnetic field produces a current that's going to try and resist it. This is why we wrap the coil around here. As the magnetic field is going up and down, you are going to be generating a current throughout this wire with a voltage Vs. So the primary is our source alternating current. The secondary is our output alternating current. And our output alternating current has a different voltage than the primary. But exactly how does this work, mathematically speaking? This is where, here this is output AC via induction. Output alternating current via induction. And the answer is going to be through Faraday's law. The exact relationship between Vs and Vp. Faraday's law we discussed was the electromotive force is equal to negative N, change in magnetic flux, divided by change in time. Here, N, remember this is from the solenoid. No, not from the solenoid. But the N is the number of turns of the wire. Number of turns of the wire. So what we're going to be doing is applying this expression to both sides of our transformer. The electromotive force, remember, is simply our voltage. And so on the primary side, we have Vp is going to be equal to negative Np times delta flux delta T. On the secondary side, we have Vs is equal to negative Ns delta Pv delta T. Now this is a magnetic field going up and down. However, we can also call this the magnetic flux. The same thing is happening with the flux also. So the flux on the primary side and the secondary side, how are they related? The flux of the primary and the secondary. What is the flux? Yeah, they're the same. This entire flux is generated by the primary side. And it's going throughout the entire sample. So here we have delta Vv or delta T is the same for the primary and the secondary sides. Now with that, we can solve for Vs and Vp by setting these equal, or setting the delta Vb, delta T equal. And what we're going to get is Vp over Np is equal to Vs over Ns. Or simply put, the secondary voltage, which is our output, is going to be Ns over Np times Vp. So how do you get a different output voltage? All you're doing is changing the number of turns. If you want a higher output voltage, you use more turns. If you want a lower output voltage, you use less turns. And so the voltage gain or drop is simply provided by the ratio of the turns of primary to the secondary. And that is all that's constituted in a transformer. And you do see these along your power lines, so on and so forth. Now they don't all have the this shape. This is just more for a teaching basis. This is for sure not the optimal. So you guys can look out what transformers look like, typically speaking, on Wikipedia. Or just on Google. So we pretty much talked about some of the main elements of how electric companies provide power to our homes. We talked about the generator as well as the transformer so that we get the proper voltage. Now the final topic we're going to look at consider the logical conclusion of some of the phenomena that we've discussed. First, we discussed that current generates a magnetic field B. Another way to put it is a change in E or delta E generates a magnetic field B. Second, is a changing B generates a resistive current. A changing B generates a resistive current. Or another way to put it is changing B generates a resistive delta E. So current generates a magnetic field. We discussed that. You use the right-hand rule, right? Current and the thumb. Current with the thumb. The curl of your fingers is a magnetic field. And changing B generates a resistive current. This is simply the idea of induction that we've been discussing. Induction. Yeah, question.
Why is it described as resistive?
Because induction generates current that's going to resist the change in B that caused it.
Okay.
Remember, this is why when you drop that copper through the tube, drop the magnet through the copper tube, what happens to the magnet? It slows down, right? Because induction is generating a current that's trying to push up the magnet.
Because it's generating a current that and the magnetic field generated by that current tries to oppose the effects of the other original magnetic field.
Original change in magnetic field, yes.
Oh, right, okay.
Original change in magnetic.
Okay.
Yep.
Thank you.
So we're going to apply that onto a graph where we do need the full 3 dimensions. Now, before I do this, I do want to say, for pretty much the entire magnetism section, I care way more about the qualitative aspects. Okay, qualitative aspects. So as long as you're able to answer the conceptual questions, that's kind of what I'm looking for. If there is a quantitative question, it's going to be there's not going to be like this 10-step problem. Okay, it's going to be like one of those 1 or 2-step problems. Because I do have to keep you guys honest and make sure you guys are actually studying everything, not just the conceptual aspects. But the conceptual aspects are very important. So let's just go over how this works. So what we're going to be discussing actually is pretty vast and very complex. So you're just going to have to take my word for a few things until we cover everything, and then we're going to come back at the end, and then I think at the end it's going to make a lot more sense. So let's say there was something that changed, that caused a change in E, like the following. Change in E. Now this delta E is going to generate a magnetic field B. This delta E then is going to generate a magnetic field B, and it's going to be in the Z direction. We'll call this B. But guess what? This magnetic field was just generated. So this is also equal to delta B. Because originally there was no magnetic field. But what did we discuss? A changing magnetic field B generates a resistive delta E. Resistive delta E. So at a later point in space, this delta E, instead of it continuing to try to shoot up to twice its height, so originally if we came here, if we were to add this on top, then this would be, we'll call it twice that. This delta B is going to make sure that this delta E doesn't go up as high. It's going to go up slightly smaller. So this is going to be smaller delta E. Because naturally this delta E wants to just keep propagating on its own, but we discussed a change in B generates a resistive delta E. Oh, sorry, resistive delta E. So the next change in the electric field is not going to be as great. The next change is not going to be as great. But guess what? We have this now change in electric field. What does a change in electric field do? It generates a magnetic field. So this was our original magnetic field B. And naturally it will want to be twice its own. However, this delta E is smaller than this delta E, so it's not going to come up as much. So then this is then going to be our delta B the next time around. Then slightly later over here, this delta B is smaller than this delta B. So the amount that it's extended is not going to be as high. So the change is continuously getting smaller and smaller and smaller. So we have that. And eventually, notice this is getting smaller, eventually it's going to curl back down onto itself. And so we get it back down to here. And at a later point in time, it goes back down to here. There. At a later point in time, it's actually just simply going to cross 0. But this is going to continue to propagate, and so it's eventually going to point down further and further, and so on and so forth. So if we connect everything, just connect the endpoints, what is it going to look like? What's the shape of this?
It's a sine wave.
It is a sine wave. And what is the shape of this? Oh, I forgot to draw here. It is also a sine wave. So in the green is the magnetic field, in the blue is the electric field. The B, the magnetic field, is propagating on the XZ plane. Whereas the electric field in blue is propagating in the XY plane. Now let me just briefly replicate this with some of the minor details omitted. And so here we still have the same coordinate axis. That all the electric fields are going up and down like this. Whereas the magnetic field going like that. So one is going up and down, let's say the whiteboard, that would be the electric field. The magnetic field is going in and out of the board, in and out of the board. So here we can gather a few pieces of information. All I did was say something caused this delta E to happen, this change in electric field. This change in electric field turned into a wave. So electric wave. But when this electric wave was generated, what happened? We got a corresponding magnetic wave. And this magnetic wave is what led to the electric field, electric field actually turning into a wave. So we can say electric wave is a magnetic wave. Also, we can say a magnetic wave is a electric wave. So electric wave is a magnetic wave, and a magnetic wave is an electric wave. Meaning, electricity and magnetism are one and the same. Called electromagnetism. This is why I've been saying those weird statements like poles and charges are not the same. Except they are. And this is why. Electricity and magnetism are a single occurring phenomenon. However, you can break it down into its further parts of electricity and magnetism, at which point they can become distinguishable, but they are very intimately related. In essence, by a long list of connections, they are one and the same thing. Because charges generate magnetic fields, and magnetic fields make them move, but then the changing electric field generates magnetic fields, so on and so forth. So electricity and magnetism are one and the same phenomenon called electromagnetism. Now there's a natural follow-up question, and that question is probably the one that you guys are all thinking about. Who cares? Who cares if that's the case? Who cares if an electric field generates a magnetic field? And that they're one and the same thing. Or sorry, electric wave generates a magnetic wave, and that they're one and the same thing. And the answer is you should. Because, do you guys remember the Aurora Borealis discussion? You guys remember that? So if you want to briefly flip back to the general schematic, remember solar flares generate these charged particles, and when it hits the magnetic field of the Earth, the charged particles are guided towards the North and the South Pole. So you guys remember this? But what actually gave the Aurora Borealis's color?
The jumping of valence electrons?
The jumping of valence electrons. I said that leads to the light. All right, but how? If you guys were students, maybe you guys would have known I cheated. Because I actually didn't give you the answer of how the electron excitation actually leads to light. This is going to help make that full connection. So because of electron excitation and relaxation. Now we're going to use the schematic of the atom, so that's the nucleus. And then I'm just going to draw a small portion of the electron orbitals. So an electron begins here. And in terms of electron excitation, you can excite an electron when light comes and activates that electron so that it jumps up to a higher orbital. But when this happens, let's actually think about what's occurring. I'm gonna get rid of the atom itself and let's just focus on the electron. Initially, the electron was here. So initially, the electron was here. Finally, the electron's going to be up here. Because this is an electron, when the electron is here, what does the electric field lines look like? What do the electric field lines look like? It's just an electron.
Still points towards the electron.
All right, they all point towards you. Well, let's just limit our focus onto a single one of those electric field lines, and let's just focus on the one that's pointing to it like this. There's other ones converging, I understand. Let's just focus on one for the purpose of our analysis. But what about when the electron gets excited? What is the electric field line going to look like then? What is up here?
Same thing.
So we'll call this E initial and we'll call that E prime. Unfortunately, there are many series of events that happens in between. Because the electron gets excited very, very quickly. Right? Quantum physicists say it actually teleports. It never actually travels through the space in between. So this to this jump happens instantaneously. But the electric field doesn't go from here to here. What happens is the moment the electron teleports over here, the electric field line looks like this for a moment. So this is, we'll call it T naught. T naught. So initially, the moment it jumps, the electric field lines, because guess what? Infinitely far away. Are you going infinitely far away? Are you going to know that the electron moved? No, because it takes some time for that information to actually pass. So what we're doing here is you can think of, grab a rope. Let's say you tie the rope onto something over there, and then you pull it until the rope is very taut. Can you guys visualize that? Can you raise your hand if you can? You just tie a rope, pull some tension on it so it's kind of like straight. What happens if you raise that rope up? What's going to happen to the rope? Is it going to move as a rigid rod would, where it starts here and then it does this, that, and then that? Or is it going to start doing this, then it's going to do something that looks like this, right? That's essentially what's happening here. When the electron goes up, the electric field very close to it does get impacted, but further away, it doesn't know that the electron jumped yet. At a later point in time, the electric field lines are going to look like this. This would be, let's call it T1. So the fact that the electron moved, that information is slowly progressing throughout time. At a later point in time, it's going to look like this, T2, and eventually, and it's going to happen as, we'll say this is at T infinity. Now this is only in the excitation portion. When the electron gets here, is the electron happy being at a high energy state? The answer is no. So the electron from here is going to jump down as part of the relaxation. We're going to do the same analysis. We're going to look at the initial, and then we're going to look at the final. So initially the electric field was here, and well, this is of the relaxation, right? And this is going to be the final electric field of relaxation. But when it jumps down, it's going to do a similar type of progression that looks like that. This is T0, T1, T2. This is T infinity. So here, the electron jumps up and then comes back down. Electron jumps up and then comes back down. So let's actually draw a coordinate system. Where here, this is, we'll say, y relaxed. We'll call this y excited. So originally, it jumps here, and so we're going to have a electric field that kind of looks like this. Right? It jumped up, we're going to have the delta E. But when it relaxes, it's going to go from here all the way down to here. So the electric field is going to look like this. Now when light comes in, electrons get excited, relaxed. That's true, but this happens as a continuous cycle. Because as light is being shown, electron excites, relaxes, many times per second. So the electron is excited, relaxed, but this information is propagating out, right? It's sending the information from here, and it's continuously going out until as time increases. So the information is propagating out. And the shape that occurs is going to be our sine function. And that is what we have drawn here. So the change in electric field constantly looks like this. But what did we discuss? When there's a change in electric field that makes an electric wave, you're also generating a corresponding magnetic wave in the y-axis. Oh. looks like that. So when the electrons are being excited, or excited up here, and then relaxed, what's the information or what's changing is light is being distorted in this fashion, and it's traveling in this direction. So this information is traveling that direction with some speed v. With some speed v. But what is this v? How fast is this actually traveling? But how fast is a wave traveling? When I raise the rope, I'm sure you guys have done this before, you know, with the rope, you just kind of swing it side to side. Have you guys done that before? Right, something along those lines. You'll notice that the little wave it does, it takes time to actually travel there, and then it kind of bounces back. But it does take time to go from here to the end of the rope. That's the same thing going on here as it's going up and down. How fast is that actually moving? And the answer, I'm going to do a very crude derivation. Yeah, I'm going to do a very, very crude derivation. So let's begin with some known information. What is true at max speed?
Acceleration.
We're told what?
Acceleration 0.
Yeah, acceleration is 0, so we also know that F net is equal to 0. We also know this to be true. Now here, well, so we know this to be true because it's the maximum speed. Well, let's look at the force balance. What are the different forces that are active? We have electric field and the magnetic field. So we have a force contribution from the electric field, plus we have a resistive contribution from the magnetic field. So let's call it negative F magnetic. Magnetic is resistive, so that's why it gets the negative. And because it's at maximum speed, we know that this has to equal 0. Because this is equal to 0, we know that F electric has to equal F magnetic. Now we just need the forms of these two expressions. What is the force from the electric field? And that is simply Q times E. What about the magnetic field? This is equal to Q times V cross B. Q times V cross B. Well, what is the magnetic field B? Now, due to cancellation of classes, I did have to skip a short section in the magnetism portion, and apparently that's when I gave this equation. But the equation is mu naught Q I over 4 pi times L cross R over R squared. Mu naught Qi L cross R over 4 pi R squared. Now this looks like a doozy. You're just gonna have to take my word for this. But it's not in a form that we like, and we can always remind ourselves, you can multiply this expression by 1 without changing the identity. But instead of 1, what we're going to multiply by is epsilon naught over epsilon naught. Now, why do we do this? Well, let's rearrange the variables around and see what we actually get out. This I times L is also V. I times L is also V. So what we get mu naught times epsilon naught times Q over 4 pi epsilon naught R squared times V cross R. Any guesses as to why we multiplied epsilon naught over epsilon naught? Does the term in the parentheses look like anything? Huh?
The value of K.
No, K is 1 over 4 pi epsilon naught. But in the parentheses, Q over 4 pi epsilon naught R squared. No, that's not epsilon naught. Yeah, it's the electric field. It's the electric field strength. Now we're going to rearrange this a little bit further. So this is going to be mu naught epsilon naught times V cross Q over 4 pi epsilon naught R squared times R. This entire term with the vector is simply the electric field. So what the magnetic field is equal to is mu naught epsilon naught V cross E. That is what the magnetic field is equal to. Mu naught epsilon naught V cross E. So we plug it into here. So then the magnetic field, the force, the magnetic portion from the force, then is equal to QV cross the magnetic field term that we just derived here is mu naught epsilon naught V cross E. can take out the constant, so it's mu naught epsilon naught times Q V cross E. V cross E. Alright, then we can plug it into this expression here. Therefore, Q times E, that's the electric field part, is equal to the magnetic field part, which is mu naught epsilon naught Q times V cross E. Now the Q's can cancel. Let's just consider the x coordinate, okay? Just in the x direction, because that's the direction that the wave is propagating. So we get E, cosine of theta, we'll call it theta A, just for arbitrary purposes. This is going to equal mu naught epsilon naught. Who remembers what the cross product is? The magnitude? A cross B is equal to AB sine of the angle theta. So this is going to be equal to V squared E sine of theta 1 times sine of theta 2. But we only want the x coordinate, so this is going to be times cosine of theta A. So what can cancel? Cosine of theta A. What other can cancel? The electric field can cancel. Sine of theta 1, sine of theta 2. Look at the direction between the electric field and the velocity. Electric field and the velocity is what direction? So the velocity is this way, electric field is up. What is the angle between them?
90.
Yeah, it's 90, so sine of theta, that's 1. And you can see that pretty much everything is 90, right? And so this is also going to be 1. So what we get then is that 1 is equal to mu naught epsilon naught times V squared. Or simply speaking, V is 1 over the square root of mu naught times epsilon naught. Can somebody take out their handbooks and their calculators and tell me what that evaluates to? What is the number? What is the corresponding number? Who's doing it? So there's a psychological phenomenon where when a crime happens and there's like 3 people, you're more when there's a crime, you're more likely to get a 911 call if there's 3 people than 1 million people. Because when there's 1 million people, everyone assumes what?
Everyone's dead.
Yeah, somebody else is gonna do it. When there's 3 people, it's very clear, oh, it's gotta be one of us, and then the cops get called. I think we're kind of at a similar scenario. Where
Yeah,
everyone's like,
someone else
well,
can do that.
somebody's doing that, it's not me. is that number? Did you get it?
No.
No? You guys aren't playing games under camera, right?
I don't know.
Kind of.
I got 3.39 times 10 to the negative 9. But I don't think that's right.
That is incorrect.
We did put it in wrong.
I got
299 million.
Oh wait, this is wrong.
299 million. Or 2.99 times 10 to the 8 meters per second. Does anybody know what this number is? This is the speed of light.
Oh, for sure.
This is why the aurora borealis, we see light when there's electron excitation and relaxation. When it gets excited, you're generating this fluctuating electric field. That fluctuation is happening at the speed of light, which tells us, okay, this fluctuating electric field is light. So, I think I got rid of it. Electric waves generating magnetic waves and so on and so forth. This tells us light is an electromagnetic wave. And this is how we can see color. We see color because of electrons being excited and relaxed continuously, so on and so forth. This is how we see the aurora borealis. This is how we can see the sun. This is how we see pretty much everything. And our eyes, our receptors, are operating in this fashion. When light comes into our eyes, our receptors have electrons that respond to the light that's actually coming. How does the electron get excited in the first place? It's because the electric field is kicking up the electron because there is a electric field component to it. Okay. So this is the final section on electromagnetism. All right, with the remainder of time, oh, by the way, actually, one second. Well, we're not done yet. Unfortunately, this derivation is wrong.
Yeah.
You won't find it probably on your textbook, although I didn't look at yours specifically. It's because it's fundamentally wrong. However, it did lead to the same answer, and that's why I'm showing it. To do it the correct way, you need essentially equivalent of calculus 4, which is obviously, beyond the scope of this class. But I still wanted you guys to see some relationship of the speed of light to the electricity and magnetism forces. If somebody spots the error in this, I'll give the entire class an extra credit point, which will be added to the midterm. What is the issue here? There is a fundamental issue.
When you put B in there.
When I put B in there? No. No.
Come on, Steve.
So one of the angles, well there's sine theta 1 and sine theta 2. Is one of those angles not 90?
No, that's fine. just to prove that to you, we first do V cross E, right? Right hand rule. V cross E. V cross E. Well, actually, I guess that is an issue too. Right.
Yeah.
Oh yeah! Let's go!
Well, you don't have to review it anymore.
Man, I
Ah,
know
that's
what
a that's an error I assume was okay. I did this in my head.
So 2 points are up for grabs.
I guess. All right, that's fine. 2 points up for grabs. What is the second?
Wow.
What is the second? Wait, V cross. Oh no! It's
Oh,
wait.
don't look too far into it. It's okay.
That's the board.
It's okay, man. Don't look too far into it. You're good.
Yeah, I'll give it. I think that is an issue. But there's a more pressing issue which pretty much negates that in the first place.
Wait, so
That's
look
kinda why
before
that
it.
is
Look
fun.
before.
I wasn't thinking that. The other section wasn't able to get it. I'll give you guys 30 more seconds.
Well, no, they don't get it. just throw that out
If I
there.
give you an infinite amount of time, you literally ask, well, is that the issue? No? Alright, is the step previous an issue? Well, no. Okay, is the step previous an issue? Yeah.
Wait, we're looking at Q, but light isn't a particle.
Huh?
It's the Q that caused it.
Oh, okay.
It's the charge that caused it. Okay, actually, but yeah, you know what? That you got the heart of it. Light is not a particle. We were wrong from here. That's where we were wrong.
Oh,
Why?
VZ ended it with saying it's a wave, and we started it with it being a particle.
Yes. Forces have to act on what? Act on a body. Light doesn't have a body. So it's a force on what? Nothing. This derivation was wrong from the very beginning.
Got it.
That's the issue. That's why, yeah, pretty much a lot of these other stuff are wrong. Right.
Actually makes
Light
sense.
is not a particle. That's the answer.
That actually makes sense to me.
Alright.
No way.
So I'll add 2 points to everybody, but that brings. Okay, we're not done yet. But the remainder of time, we do have to talk about something likely all of you guys want to talk about, which is the midterm.
Yes, sir.
I'll forget the exact distribution for you guys. I think the high. I think this is correct. The high was less than an 80. If one of you guys got higher than an 80, let me know because I'm misremembering this. The average, I'm forgetting that too. Hold on, let me just look at it. Oh, by the way, you guys can't get it back yet because not everyone's taken it. Not from you guys, but from the prior section. And because there's like overlapping questions, I can't hand those back. Oh man, it was.
Waiting.
It was lower than what I thought what I was about to write down. The average was a. Yeah, the average was a 48. I did mention at the very beginning that this is probably the material-wise, probably the hardest material that's being taught at this course. I still do stand by it, because in my mind, I still didn't really ask difficult questions. I mean, there was 1 or 2, but definitely not to explain the 48. So let's have a chat. Well, what does a 48 correspond to? What letter? Right, this for me would correspond to a 58, which is still, we'll call it F plus. Call it F plus. Alright, let's have a chat. You guys wanna request anything?
Can we get more points?
Well, actually, remember you guys just got 2 points.
Yo!
Oh yeah, so +2, that's 50, and then it'll turn, so it's a D minus actually.
This looks good.
By the way, the earlier section got 0 points from that exercise. They didn't get it.
How many points did they get total?
So their average, I would say they had a significantly harder exam than you guys. Like I copied and pasted one of the quiz problems or something onto yours. For them, I made a brand new problem which was much harder. Even then, their average was a 61. So theirs wasn't too hot either. But I'm gonna do one for you guys. Even though their average was much, much higher, they would not stop bugging me. Even after I'm like, wait till class, I'll talk about the distribution, I'll talk about the average and everything. And people were just bombarding me with questions and asking for a curve and things like this. Even though you guys did much worse, you guys stayed patient, so I will reward you guys. Unfortunately, I'm not going to curve. I'm not a huge fan of that. Instead, I would much rather prefer if you guys earned your grade also in preparation for the final. For the earlier section, man, I wasn't going to do anything to them because they were bugging the heck out of me like no crazy. I was super crazy. I let them redo one problem from the open resource problem or open resource section, and then they'll get the points back, the difference. So if they got a 4 out of 11, and then they redo that problem and get an 11 out of 11, they're only getting 7 points. Does that make sense?
Mm-hmm.
You can redo the problem that you dropped, and then you'll get the full 11 out of 11 points back. For you guys, I'll let you guys redo 2 problems. 2 problems of your choosing. Does that make sense?
Yeah.
And then I'll modify the scores to your grade. Yeah. Yeah, so, no, not in lab. I'll let you guys, even though you can't take it home, I'll let you see the exams in the lab. Whatever problems you guys decide to do, just take a picture. Now, here's the thing, because not everyone has taken it, and also, you guys shouldn't be, showing the exam to like future classes either. You guys need to give me at least a verbal confirmation that you guys are not going to be doing either one of those things. Then I'll let you do this, so you'll just take a picture during lab on Thursday, and then it'll be due next Monday. Does that make sense? So you have the entire weekend to redo it. Also, I am alleviating the exam required, or exam strictness, or whatever, exam rules. You are allowed to discuss with other people. Okay? So this is a collaborative environment. However, you are not permitted to simply copy and paste somebody else's work. You have to understand what you actually put down. Does that make sense? So that's my rule, and I'm just hoping you guys are of character enough to kind of, at least try to do that. Okay? As long as you try to do it, we're on the same definition here. So as long as you're able to kind of explain why you wrote down everything, we are good, and you are permitted to collaborate with whoever you like, but not the internet. So it has to be, somebody on campus, textbook, things like this. Does that make sense?
Mm-hmm.
Make sense to everybody? So if everybody does it, potentially, you guys are going to get 22 additional points. Right, because each problem's worth 11. If you do 2, the average can easily get you back up to a 7. And I did really appreciate you guys. I don't think a single person reached out to me. All right, maybe you guys just gave up and that's fine. But the other section, man, I got so many emails that I'm traveling, and I'm trying to focus on other stuff, and they're just bombarding me with questions and and here's the thing: lucky for them, I was not going to even give them this like problem redo, but some people actually reached out asking for advice, and that was their saving grace. Because if they didn't do that, and people were just asking for a curve, I was like, okay, you want free grades? Okay, that means you do not deserve anything, right? But luckily, some of them actually reached out for advice, and that's why I let them do one problem. Question?
When you were saying that we all need to do that, do you mean that like we won't get the points back unless everybody in the class does it, or as long as we submit the 2 columns, we'll get it back on our score?
Yeah, as long as you do it.
Okay.
Yeah.
Sorry, you made it sound like for a second that like if everybody didn't try to do the 2 columns, we wouldn't get the points back. But never mind.
No, if everybody does it, then the average goes up by 22. And everyone gets it correct. You can get up to 22 points back in terms of the average course, or average for the course, which is really high.
So we don't have to, we can choose it, two any problems, it doesn't have to be the ones that we dropped, right?
Yes, it could be any two, but remember, you're only getting the points back that make up the difference. So if you got a 4 out of 11, you redo it, how many points are you getting back? 7. Right? You can't do one that you got 11 out of 11 on, and then expect to get 11 more points out of that. No, it doesn't work that way. It's one of the problems you got wrong, but the one you dropped is permitted as well. Okay? But you'll be able to see that on Thursday, okay? And other than that, have a great week.